When a weak base, and we'll represent base with a B, dissolves in water, it reacts with the water in a similar manner as a weak acid. So our base B reacts with water molecule to form an equilibrium with its conjugate acid and a hydroxide ion. Many weak bases contain a nitrogen atom, and a nitrogen atom has a lone pair of electrons. So this lone pair of electrons allows nitrogen to accept an H plus ion from an acid, which it does, forming a coordinate covalent bond. So here comes our H. It has no electrons, so it has a plus charge. And that's how you form an ammonium ion. An example is ammonia plus water will form an equilibrium with ammonium and hydroxide. So ammonia is the base because it accepts a hydrogen ion, and the ammonium ion is the conjugate acid of the weak base. Ammonium will give up an H plus in water to form ammonia, so that's why it's an acid. So basically, there's your base, there's your acid, there's your conjugate acid, there's your conjugate base. The equilibrium constant, or base ionized constant, is now written as a Kb. So your Kb is equal to the concentration of your conjugate acid times the hydroxide ion concentration all over the concentration of your base. So in terms of the ammonia reaction, the Kb would be equal to the ammonium ion times the hydroxide ion all over the base ammonia concentration. So problems for weak bases are exactly the same as the problems for weak acids. You can have a Kb, Ka, pH, percent ionization, but with bases it requires one extra step, because in order to find pH, you go from the hydroxide ion concentration to an H plus to pH, or hydroxide to POH to pH. What is the pH of a 0.1 molar solution of hydrazine, a weak base with a Kb value of 1.7 times 10 to the negative 6? So first of all, you have to write a balanced chemical equation. So hydrazine plus water. So this is a standard way to write a equilibrium reaction for a weak base. Now, if the hydrazine is a weak base, that means it accepts an H plus from water. So N2H5 now, and with a +1 charge. And the water has donated an H plus, so it's left as an OH minus. So there we go. Add an H plus to your base formula, and the other product is the hydroxide. So to do this question, we have to set up our Kb expression and an ice table. So the Kb will be the concentration of our conjugate acid times the concentration of the hydroxide ion all over the concentration of our base. So initially we have 0.1 mole per liter of our base, no product yet. They go through a change, so the coefficient times x. So then we have 0.1 minus x, x, and x for our Kb expression. So 1.7 times 10 to the negative 6 is equal to x times x, or x squared, over 0.1 minus x. Now, remember, we're chemists, we're efficient, so 0.1 over 1.7 times 10 to the negative 6. If this is much greater than 1,000, then we can assume that 0.1 minus x is approximately 0.1, and it is. So that simplifies our work. 1.7 times 10 to the negative 6 is equal to x squared over 0.1. So x squared is equal to 1.7 times 10 to the negative 7. And now find the square root of both sides, and that will give us our value for x. So x is equal to 4.12 times 10 to the negative 4 moles per liter, and this is equal to the hydroxide ion. So at this point you've got two avenues. You can either find pOH, the negative log of that value, and then pH will be equal to 14 minus pOH. Or you can take the hydroxide ion concentration and find the H plus ion concentration by taking 1 times 10 to the negative 14 divided by the hydroxide, and then take the negative log of your H plus ion concentration. So negative log of OH minus is for pOH. So either way, you're going to get an answer. So I'm going to just take the negative log of this number. So pOH is 3.385. And then the pH is 14 minus 3.385. So that's 10.615. Sometimes people forget and they end up with this value and think that it's the pH. We know it's a base, so your value should be greater than 7. So this is always a good place to check. Does my answer make sense? In this case, no, it didn't. Forgot a step. Now the pH is greater than 7. Sometimes we're interested in the conjugate base of a weak acid in solution by itself. For example, the acetate ion. It's the conjugate base of the weak acid acetic acid. The IUPAC name for acetic acid is ethanoic acid. So it's really the ethanoate ion, but it doesn't matter which one you use. So in this case, the Kb will be equal to the concentration of acetic acid times the hydroxide ion concentration all over the concentration of the acetate ion. Now, it could very well ask in a question, what is the pH of a 0.1 molar solution? But if you look up the acetate ion in your table, perhaps you don't find the acetate ion in your table of K values for bases. But there is a relationship between the Ka, the Kb, and the Kw. The Ka times the Kb is equal to Kw, which is 1 times 10 to the negative 14. So if you have the conjugate base, and you can find then the Ka value in the table of K values for acids, you can determine the Kb. So in this case, the Kb is going to be equal to 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So the Kb value is 5.55 repeated, or 56 times 10 to the negative 10. So if you can't find a Kb value, but you can find the Ka, use this relationship to determine the value that you need. Okay, what's the pH of a solution of 0.1 molar cyanide ion? So cyanide, so this is the conjugate base of hydrocyanic acid, otherwise known as hydrogen cyanide. So plus water, double arrow, HCN plus OH minus. So we're going to need an ice table and a Kb expression. So initially 0.1 mole per liter, no products, change coefficient times x. So we're interested in this line. Kb is equal to HCN times OH minus all over Cn minus. So this is equal to x squared over 0.1 minus x. Cn minus is not in my table, so I have to find the Kb. So 1 times 10 to the negative 14 divided by my Ka value. 6.2 times 10 to the negative 10. So our Kb is 1.61 times 10 to the negative 5, or 1.6 times 10 to the negative 5. So 0.1 divided by 1.6 times 10 to the negative 5. If that is much greater than 1,000, then we can say 0.1 minus x is approximately 0.1. And it is. It's 62,000. All right, so here we go. 1.6 times 10 to the negative 5. So x squared is equal to 0.1 times 1.6 times 10 to the negative 6, because 0.1 times 1.6 times 10 to the negative 5, which is 1.6 times 10 to the negative 6. Take the square root of both sides. X is equal to 1.26 times 10 to the negative 3 moles per liter. And that is equal to the hydroxide ion concentration. So if I find the negative log of that value, My pOH is 2.90. So my pH is 11.10. So the pH of a solution of 0.1 molar cyanide ion is 11.10. So it is basic, right? It's greater than pH of 7. So basically, Ka, Kb, very similar. You approach the questions the same way as we did with acids, finding pH. You can do percent ionization, take the hydroxide ion concentration. In this case, I'll just pop it up here. We said 1.26 times 10 to the negative 3 moles per liter for hydroxide. We had 0.1 to start. So our percent ionization is about 1.3%. So not very much ionizes at all. So you've got your Kb, you can find pH, you can find percent ionization. It just takes one extra step to figure out your pH.